Limits at infinity, and a little bit beyond, a la Shmoop. Astronaut Buzz Goodyear and his crew have encountered a foreign galaxy, and within that galaxy, a unique solar system. Buzz has calculated equations to represent the gravitational patterns of every planet in the system. Each equation has the format h equals f of t, where h is the height in meters of the ball above the planet's surface at any given time t, where t is the number of seconds passed after the ball first hit the ground. Be sure you figure out what all these letters mean because they're really important for this opus. That is, he'll know how the function h behaves as t approaches infinity, yes, and beyond. The first planet has a gravity equation of h equals 2t. 1 second after the ball hits the ground, it's at 2 feet. After 5 seconds, the ball is at 10 feet. At a minute, it's at 120 feet, and so on. As more and more time passes, that is, as t approaches infinity, the ball will reach an infinite number of meters above the planet. Therefore, in math terms, we can say that as t approaches infinity, h also approaches infinity. The general rule with functions like these is that if t is raised to a power greater than 0, h will approach infinity. The second planet has an equation of h equals 1 over t. We can rewrite this equation as t to the negative 1 power. That means at 1 second after hitting the ground, the ball would be 1 meter off the ground. At 5 seconds, the ball would be 1/5 of a meter off the ground. As time passes and t approaches infinity, h gets smaller and smaller and really close to 0, but the ball will never actually touch the ground. So as t approaches infinity, h approaches 0. The general rule with functions like these is that if t is raised to a power less than 0, h will approach 0. Now here are the 3 planets in the same orbit, each with completely different gravitational laws. We can make general rules for limits that go to infinity based on the powers of the leading terms of the numerator and denominator. If the power of the numerator is less than the denominator, then as t approaches infinity, h approaches 0. This is true because the denominator increases faster than the numerator. Let's test this. The first planet in this orbit has an equation of h equals t over t squared plus 1. If we plug in t equals 1, the numerator is 1 and the denominator is 1 squared plus 1, which is 1 plus 1 or 2. At t equals 10, h equals 10 over 10 squared plus 1, which is 100 plus 1 or 101. If we continue plugging in bigger values for t, the fraction h gets smaller and smaller. So as t approaches infinity, h approaches 0 but never actually equals 0. The second planet in the orbit has an equation of h equals 4 t squared over t squared plus 1. The powers of the numerator and denominator are the same, so we have to do something different. Here we can just take the coefficients and divide them by each other to get the limit. We can take the leading coefficient of the numerator 4 and divide it by the leading coefficient of the denominator 1. So to get that limit of h as t approaches infinity is 4 over 1, or 4. Finally, the third planet in the orbit has an equation of h equals 2t cubed over t squared plus 1. Since we're taking the limit as t approaches infinity, we can just divide the leading terms 2t cubed and t squared to get an accurate approximation of the limit. We can ignore the plus 1 because everything besides the leading terms is negligible since the leading terms determine the behavior of a polynomial at infinity. 2t cubed divided by t squared equals 2t. We can plug in infinity for t to get 2 times infinity. Infinity isn't really a number, so multiplying it by 2 just leaves it as infinity. There's no such thing as like double infinity. So the limit of h as t approaches infinity is also infinity. As a recap here, the general rules for rational functions are: if the power of the numerator is less than the denominator, then as t approaches infinity, h approaches 0. If the power of the numerator and the denominator are the same, then as t approaches infinity, h approaches a constant, specifically the number achieved when the leading coefficient of the numerator is divided by that of the denominator. Check this out. And finally, if the power of the numerator is greater than the denominator, h approaches either negative or positive infinity as t approaches infinity, depending on the signs of the leading coefficients of the numerator and denominator. There are many rules, but it's vital to remember that infinity is not a real number, but a concept, just like forever, or eternity, or no taxes, I promise. But if it helps, you can think of infinity as representing a really big undefined number. Seems like Buzz is going to have to take his crew elsewhere, though, preferably a galaxy where gravity isn't so bonkers. This isn't how he wanted to lose weight.